So image enhancement, image restoration, and morphological processing are the steps at a lower level, which are attempting to make the image with a better quality and naturalness. Once we check the quality of the image, the next step is image analysis. During image analysis, the first step is segmentation. Segmentation is the process of partitioning the image into the focused areas, pictures, starting from identifying the foreground and the background. We have to also identify the multiple images that are available in the image. Then from those identified image, we have to represent them and describe them using the feature extraction algorithms and the feature selection techniques. So the feature extraction and the selection techniques are techniques that are enabling to represent the image such that the image is easily processed by machine learning techniques or similarity measurement techniques. So the representation and the description of the image is critical for manipulating the image. Associated images are not directly accessible. Since we are indirectly accessing, the feature extraction and selections are critical for representing and describing images. When we are representing and describing the image, basically we are dependent on the content of the image. In any image, there is color. In any image, there is texture. Any image has shape and structure. Even size also. Sightings are the primitive features that we are extracting from the image, and they are used for representing the image. But in behind, you can manipulate the features. Like rather than representing by all the colors that are extracted from the image, we can create a color histogram that can divide the color into 3-4 parts as per their appearance within the object. Then we can also see how the color is transiting from one color type to another color type. That is texture identification. Even if in terms of color, two objects are the same, the way the colors are transiting may be different from image to image. So again, by adding texture, we can have a better chance for identifying one object from another object based on the representation and the description. That means we have to use a combination of attributes or features for representing and describing objects. Once the object is represented, the next step is recognition or identification or verification. We can design an iris recognition system for biometric. So by looking at a given person's iris, the system can say a person with this kind of iris is this person. Or we can design a document image retrieval system or an image content-based image retrieval system. Or we can design a system that can verify by comparing one object with another object. Or we can design a system that can identify one object from a collection of objects. Searching. So beyond these steps, image compression and color image processing are nowadays critical. Why image compression? We know we need it for reducing the memory space requirement, the transmission bandwidth requirements of an image. In addition to image compression, which can help us to store as many images as possible, nowadays, since most of the images are captured, digitized, and stored using colors, So most of the image that we have is a color image. And rather than dealing with binary image, grayscale image, it's better to deal with the color image as it is. For that, color image processing is required, because the color image is not like a grayscale image with finite number of colors. The color image is not the same as monochrome image. So color images are requiring more better effective algorithms. Otherwise, they are making the system more intensive memory-wise, processor-wise. So how can we deal with color image? How can we process them? How can we extract features from the color image? Because the red color, the green color, the blue colors are a combination that are forming a given color. So by extracting those representations in terms of color, will make the image representing in a natural way, just by extracting whatever colors are available in that image. If you go for texture analysis, again, it can be done in a natural way, since we are looking at how within the image there is a transition from one color type to another color type. So nowadays also color image processing is an active research area. So in any case, the major task in digital image processing is image restoration and image enhancement, especially image restoration. In any of the images that we are capturing, even if it is looking like with good quality and the naturalness, if you view the image using image viewers like GIMP, GIMP, you will see the quality. To what extent the noises are available in a given image. So such challenges from the satellite images or the medical images or the images that are captured from agricultural products should be first of all checked for their quality, whether they are free from noise or not. For that, there are different approaches available, especially the image filtering approach. So the major goal of image restoration is reducing the effect of noise that comes because of a digitization, because of compression or transmission. So the major aim of any image restoration is checking and improving the quality and the naturalness of an image. What is the difference between quality and the naturalness? Quality is more of how human beings are perceiving the image. To what extent human beings are satisfied with the image. As human beings are satisfied with the image becomes with a better quality. But naturalness is related to the image itself. We have to capture what we observe in the reality. A tree is with green leaves. If a tree has with yellow leaves, something is wrong. Or maybe we are capturing a dry leaf, a dry tree with yellow leaves. So we have to make sure that the naturalness of an image, whether the image that we have is the same as the real life image, the real life object or not. So image restoration is trying to make sure for us and accordingly improve whether the image is free from noise or not, and does then improve the quality and naturalness of the image. So for that, basically, as compared to image enhancement, image restoration can be objectively done. Since the image is degraded, noises are added from the external environment while you are capturing, while you are digitizing, compressing, or transmitting, or downloading, uploading. Sightings can be simulated. So a prior knowledge can easily be defined for restoring an image which is degraded by the external noise. But image enhancement can't be modeled, because image enhancement is required for an image which is captured from an object with poor quality. If the original image is with poor quality, if it's not well defining the content, whatever image that we are capturing is also degraded. It can't be objectively defined since we don't know the original image quality. But image restoration, since it is trying to reduce any degradation that comes from the external world, it can be objectively modeled. Even in MATLAB, we'll see it's possible to add noise, even sometimes to challenge the filtering algorithms. So the noises in an image can be reduced using image restoration. What are the sources of noise? As we said, when we are capturing the image, unless and otherwise we give care for the light, the internal light self, or a reflection that comes from the external world, even the temperature, even the environmental conditions are affecting when we are capturing the image, when we are acquiring the image. Especially the sensor heat should be well adjusted. During digitization also, since it is an approximation, during sampling, during quantizing, during compressing, there are different effects that are expected, especially the aliasing effect. An effect which comes because of taking non-representative number of samples. Aliasing effect is an effect which is changing our understanding of the image. While the image is something else, we may understand that image as another thing. So to reduce an aliasing effect, we have to de-alias it. We have to correct our sampling. Says that experimentally we have to adjust before quantizing. Then again, even compression is also adding noises. Still, it is an approximation using different algorithms. When we are compressing, we may lose some content. Or when we are compressing, you may change 0 into 1, 1 into 0. Even image transmission, when you are transmitting over the network, when you are transmitting using different medias, storage medias, there are an effect that comes from those medias, and they are adding noises into image pixels. While you are transmitting using the wireless or the wired, still in behind something may be wrong. So the 0 pixels may be switched to 1, or the 1 pixel may be switched to 0. That means the content internally changes. That is creating a noise.
Yeah. እስቲ በለኝ። እሺ
አረ ኖይዝ ቀንሱ።
እሺ አለ።
So during image processing, it's possible to model noises in the image. Whatever image that comes from the external world, we can model it using degradation function. A function that can add noises into the original image. So that added noise can help us to model what kind of noise is available in that image. When you reverse the added noise, you can restore and convert into the original image. If f of xy is the original image, if you are applying the degradation function h, and on f of xy is the original image, if you add noise, then the new images with some noise, g of xy. Since we already modeled it, then if you take the inverse of the degradation function and subtract from the noisy image, the added noise, will get the original image. So what kind of noise is affecting our images can easily be experimentally proved. When we are looking at noises that may happen in a given image, there are basically 4 types of noises. The major one is the salt and the pepper noise. A noise which is affecting overall the image, which is distributed over all the image. It's not concentrating at one point. It is distributed all over the image randomly. So it is scattered over the image. Basically, nowadays, the median filtering or morphological filtering can solve such kinds of problem. The median filtering is designed based on the statistical median. In the case of median, arrange the given values in ascending or descending order and identify the middle one. That middle one is maybe a pixel with noise or free from noise. So then that middle one is replacing the noisy pixel. Morphological filtering is another thing. If pixel is lost, it's trying to add pixel representing the picture, one. Or if noise is added, means the background is corrupting the picture, then erosion is applied to remove the background from the picture. The other critical noise is also Gaussian noise. Gaussian noise is a noise which is normally distributed. A normally distributed curve is maybe from the 2 ends, the image is free from noise, but the noise is concentrated at the middle of the image at some specific point. Again, this kind of noises can easily be modeled. For the Gaussian noise, there is a Gaussian filtering technique, which is depending on the normal distribution of the noise. A function is designed to simulate the Gaussian noise, says that the inverse of it will solve the problem of the effect of the Gaussian noise. The other noises are speckle noise and periodic noise, which are not happening frequently, but if they are happening, it's very difficult to clean them. Still, researches are going on around speckle noise and periodic noise. Speckle noises are noises that are affecting mostly the background. The background, while we are expecting it in black and white image, white color, it may be becoming a black color. And even that black color is not 100% black, it's a gray scale. So we have to understand the intensity of the grayscale, either to classify it as a black pixel or a white pixel. So this is requiring an understanding of the intensity level of the noises that are corrupting the background. Sometimes the background maybe looks like an object itself. When we are trying to segment and extract features, maybe the feature extraction and the segmentation algorithms are easily confused to differentiate the background and the foreground pixels. So spectral noises are frequently modeled by multiplying the pixel values by the random values. Since it is randomly happening to corrupt the background pixels, so by multiplying every pixels with some random values, we can magnify those noises which are corrupting the background to make sure that whether they are part of the foreground or the background. It's like normalization. Periodic noise, the name itself is periodic. They are happening periodically. The noises are happening because of either electrical or electromechanical interference. So the upside down of a combination of foreground and the background is happening within the image. Even if the image is available within the picture is available in the image, because of the interference that comes from electrical or electromechanical, it's very difficult to understand the patterns, the flows that are happening within the image. So this kind of image requires analyzing or filtering in a frequency domain. Frequency domain means by moving the image rather than counting the number of pixels, by understanding the ratio of the pixels. How frequently a given pixel intensity is happening at a given space. We can go salt and pepper noise, Gaussian noise, speckle noise to deal with in an n-frequency domain or in a spatial domain, but the periodic noises are better removed when we are dealing with image at a frequency domain, because there are blurred images that are resulting because of periodic noise. A blurred images are very difficult to understand them. So first of all, we have to convert them from their current spatial domain to frequency domain, where we can easily understand how frequently such intensities are happening as compared to the other pixel type. So spatial domains are domains where we can statistically analyze the image using its pixel values, where we can easily reduce the effect of additive noises by defining parameters, by creating windows through which we can easily investigate, as compared to a given point, when that pixel point is compared with the surrounding pixels. Is there any noise or not can easily be detected in a spatial domain. But it has less performance for blurred images, which is requiring to move to frequency domain. Frequency domain is transforming the image from spatial domain to another domain, where we can understand the frequency of occurrence of, not how much occurs, but the frequency of occurrence of relative to others noises within the image. For that, there are many algorithms available, like discrete Fourier transform, cosine transform. By using the frequency domain, we can start reducing the effect of periodic noise. So within the spatial domain, it is more easier to analyze the image, whether it is free from noise, and accordingly, if there is noise, to correct. But in a frequency domain, it's a little bit tougher. We don't have the chance to understand how frequently noises are happening because it's already a transformed domain. But it's possible once in a frequency domain, after processing the image, to convert it back to the spatial domain to understand the pixels and visualize it using image viewers. But whatever in frequency domain can't be visualized using image viewers. So using the different transformations, Fourier transformation, Laplacian transformation, cosine transformation, Z transformation, we can reduce the effect of periodic noise, and then we can transform back to the spatial domain, and then we can apply the image analysis and image understanding. But mostly, we are using the spatial domain. If the spatial domain doesn't work, we go for the frequency domain for applying the different transformations to reduce the effect of noise. So basically, image restoration or image enhancement means filtering the image. Filtering means nothing but to reduce the effect of noises. When we are dealing it in a spatial domain, we are trying to count by accessing the pixels within the image and by understanding what kind of pixel is occurring in a given point within the image. So basically, there are nowadays there are two mechanisms that are suggested: the low pass filtering and the high pass filtering. Mostly, again, we are using the low pass. Low pass means by understanding the image intensity, correct it immediately. Says that any rough effects of noises can be corrected. But still, the low pass may be not an end by itself in image restoration. It may require also smoothing, which takes us to the high pass. So the low passes are trying to reduce the frequency of occurrence of noises across the image. But sometimes the frequency of occurrences of noises in the images are less, but their occurrence in a given point is very high. Such things are requiring smoothing. If not, smoothing is not correcting them, we have to go for frequency domain. So basically, when we are saying image filtering, we are saying spatial filtering. Spatial filtering means analyzing the pixels that are forming a given image directly. By analyzing the image, we have to correct if a given pixel contains noises. To check every pixel, we have to have a window. A window is a mechanism of checking the image, because we can't check the whole image using only one window that covers the whole window, the whole image. We have to start partitioning the image into multiple points. For partitioning the image and checking every point, we need a window. Can we create a 3x3 window, or a 5x5 window, or a 7x7 window, 9x9 window? Is a window with a shape of box, or with a shape of cross, or with a shape of multiple sign? Those things are decided based on experimentation. But the major thing is, we are trying to evaluate whether a given pixel is containing noise or not by comparing it with the surrounding pixels based on the windows that we created. So when we are creating the window, can we go for evaluating a given central pixels P of xy by using the left, right, up and down, that's a cross window, or by drawing a box which can take all the surrounding of a given pixel, which makes a box, not only including the cross but also the diagonal lines, or we can ignore the cross and check only the diagonal pixels. But mostly, again, we are using box to check all the surrounding, all the neighbors of a given pixel in that given image. So either is that enough to check 8 pixels or 4 pixels is decided based on the experiment. But mostly checking the 8 pixels that are surrounding vertically, horizontally, diagonally a given pixel is better than just checking only the horizontal, vertical intersecting pixels or the diagonal pixels. But the efficiency is better if you are checking only the 4 pixels. But for effectiveness or accuracy, it's better to go for checking the 8 surrounding pixels given the central pixel, P of xy. That means you have to check around that P of xy. Px minus 1 y, Px plus 1 y, Pxy minus 1, Pxy plus 1, or Px minus 1 y minus 1, or Px minus 1 y plus 1, Px plus 1 y plus 1. There are 8 options around a given Pxy. Checking all those things, comparing the central pixel with all those things, then decide whether the pixel as the center is with noise or free from noise. So in a spatial domain, our filtering techniques are either a low pass filtering techniques or a high pass filtering techniques. Why we need a low pass filtering techniques? From a rough image to create a smooth image. A low pass filtering techniques are trying to analyze the image and as much as possible try to, using the window, reduce the noise within the image. Say that the rough image that are distributed all over the image, the rough noises that are distributed all over the rough image are reduced and a smooth image can be created. Like median filtering, mean or average filtering, Gaussian filtering, correlation filtering, convolutional filterings are a low pass filtering. But the low pass filtering, maybe sometimes while they are trying to reduce the effect of the noise, they may also add some noises. A smooth image doesn't mean it's clean or free from noise. A smooth image may need sharpening it, especially at the border. For that, we need high-pass filtering. High-pass filtering can be applied by subtracting from the original image an image which passed through the low-pass filtering. So from the original image, if you subtract a low-pass filtered image, you will get a high-pass filtered image. That means a sharpened image. When we are looking at the different filtering techniques, spatial noise filtering technique is one. Spatial noise filtering techniques are working within the spatial domain by checking every pixel and evaluating that pixel against the surrounding pixel. It's trying to determine whether that pixel is with noise or free from noise. You can use like minimum filtering. From the surrounding pixel, identify the minimum value. If that minimum value is the same as the central pixel, so that pixel is free from noise. Otherwise, if the central pixel is different from the minimum value pixel identified from the surrounding pixel, then we have to replace it, because the value of the central pixel is wrong. Or you can use maximum filtering. Again, maximum filtering means identify the maximum value using the max function. That maximum value should be compared with the central pixel. If they are the same, the pixel is okay. Otherwise, we have to replace the central pixel with the maximum value identified through maximum filtering. But mostly, we are not using min and max, since they are sensitive for spatial distribution of pixel values. Min filtering, median filtering are better. And you will get them with MATLAB also. Min filtering is a filtering designed based on the principle of mean. How we can calculate mean? Summation over all pixels, the n pixels that we are considering, divided by the number of n pixels that we are considering. What about the median filtering? Again, median